We're now going to look at a device called the ideal transformer. It's a simplification of the linear transformer. It makes some simplifications, and we don't end up dealing with reflected impedance. And the ideal transformer is the model that's typically used in the power system. It's not as accurate as the linear transformer. All transformers actually are linear, so this is an approximation technique, but it does simplify the calculations substantially. So before we start going into the ideal transformer, what we want to look at is kind of the construction of a transformer again. So, in most transformer devices, what we've got is we've got a core. I've been drawing it as a rectangle. Usually this is some sort of tubular metal. There is a wire that is wrapped around this to form an inductor. And what happens is there's a current flowing in here, and there's a voltage across the terminals of the wire. We're going to add a little bit of information. How many turns of wire exist here? We're going to say that there's N1 turns of wire. Similarly, on the secondary side, there's a bunch of coils of wire wrapped around there, and there's also a voltage that appears there, V2, and there's going to be a current that flows, I2, and we're going to say that on this side there's a certain number of turns of wire, N2. And again, this is called, this is the primary side, and this is called the secondary. Right? Just a little bit of review. You guys probably already know this. It doesn't help to go over it. Ideally, what is said about a transformer is that there is power conservation across this. So there's I1, V1 is equal to I2, V2. The product of voltage and current is power, and the product of voltage and current on the secondary side is power. And we know that all the voltages, the voltage level and current levels aren't the same on either side of the transformer. The power has to be continuous across the transformer device. And if we make that assumption, that's really what we're talking about when we say that there's an ideal transformer analysis. So we're going to use that, and we're going to introduce one more piece of information into the puzzle here, and that has to do with N1 and N2. N1 and N2, if we divide N1 by N2, we get what's called the turns ratio of the ideal transformer. And in an ideal transformer, the turns ratio also is the ratio of the input voltage to the output voltage, which by I1 V1 equals I2 V2 means it is also the reciprocal of the relationship of the output current, or the input current to the output current. So we see by this equation, we say that the voltage ratio in a transformer is equal to the turns ratio of the two coils, and the current ratio is equal to the reciprocal of the turns ratio. So the volt-amp product and the power on both sides are therefore equivalent, right? Indicating that condition is true. When this is the case, we typically use this electrical symbol. We've got one coil. We then draw these two straight lines. In between it, the lines representing the laminated magnetic core of an ideal transformer. And instead of indicating the mutual inductance, usually what is said is the turns ratio. For example, a 10-to-1 turns ratio, meaning there are 10 coils of wire on the primary side and 1 coil of wire on the secondary side. So this is what is meant by the ideal transformer, and the simplification is we'll use because power is constant, ignoring the resistances and such things, and assuming that all magnetic flux from N1 is coupled into N2, what we find is that all we need to know is the turns ratio. We can ignore all the losses due to the self-inductance, mutual inductance, and parasitic resistances. So that's what we're going to start working with, because this transformer model using the turns ratio is really what's most commonly applied in electric power systems. And this really is pretty easy application. So what we're going to do is we're just going to come down here and we're going to draw a really simple circuit. We've got a sinusoidal voltage source. We're going to say it's 2,500 volts times the cosine of 400t, and it has this voltage source has an internal impedance of 25 ohms, and it has an internal impedance of 5 millihenries. It is in turn connected to an ideal transformer. And the ideal transformer, all it does is serve a load that is inductive. It's a lagging load, 273.5 milliohms. And 125 microamps. Sorry, microhenries. 125 microhenries. So this is our circuit, and what we want to do is find I1, I2, and we want to find the voltage across the two primaries. And we need one more piece of information that I left out: the 10-to-1 turns ratio. 10-to-1. So what we need to do to start analyzing this, let's just convert that voltage over into a phasor domain. Vg is equal to 2,500 at angle 0 degrees. That Rs, or the R of the generator, is going to remain at 25 ohms. X of the generator, the reactance of the generator, is J times 400 times 5 millihenries. That's equal to J2 ohms. We've got R sub L, that's going to stay at 275.3 milliohms, but the reactance of the load is going to be J times 400 times 125. Sorry, I wrote microhenries here. I meant millihenries, so we're going to multiply that by millihenries, and that's J.05 ohms of inductive reactance on the primary side, or on the secondary side, excuse me. So what we're going to do is we're going to write the mesh current equation around the primary side. That's going to be 2,500 volts at angle 0 degrees is equal to the current flow, which is I1 times 25 plus J2 ohms, and instead of having to take this inductor into account, what we do is we just add V1. That's for the left-hand side. And then for the right-hand side, what we say is that the voltage across the inductor, V2, that's just equal to I2 times 0.2753 plus J.05. So that gives us the two equations that we need to use to analyze the ideal transformer. You'll notice that we don't, when doing ideal transformer analysis, we don't include the inductance of the primary and secondary coils. That's built into these voltage assumptions here, and it's one of the assumptions of the ideal transformer, is that this thing doesn't actually have any inductive reactive loss. Obviously not true, but a simplification. So now what we need to do is apply the turns ratio. Remember, V1 over V2 is equal to N1 over N2. What this tells us is we could say that V1 is equal to N1 over N2 times V2. our turns ratio we were given was 10 to 1, so V1 equals 10 to 1 V2, or V1 equals 10 V2. We also know that I2 for I1 equals N1 over N2, so again we're applying the turns ratio. This says that I2 is equal to I1 times the turn ratio, N1 over N2, and we're left with I2 is equal to 10 I1. So that's the application of the turns ratio. What we can do is we can substitute these up into the equations that we already wrote. So we're going to go ahead and do that. So what that results in is, starting with the first one, the first equation we had again was V2 is equal to I2 times 0.2753 plus J.05. So what we want to do is we're going to go ahead and substitute in for V2, that's V1 over 10, and that is equal to I2, which is just 10 I1, times 0.2753 plus J.05. So now we have this equation here, which is in terms of I1 and V1, and here we have this equation, which is in terms of I1 and V1. So we can just solve for one of the variables and substitute. So what I'm going to do is solve this guy for V1. That's V1 is equal to 100 I1 and 0.2753 plus J.05. That we can distribute that 100. That says V1 is equal to I1 times 27.53 plus J5. Right. So I've made that simplification solved for V1. I'm going to go ahead and substitute that into this equation right here. So what I get is 2500 at an angle of 0 degrees is equal to I1, right, times 25 plus J2 You know what I'm noticing is that I meant that to be 0.25, not 25. That's 0.25 ohms right there. Sorry about that. Equals I1 times 0.25 plus J2 plus V1, and we just substitute that into there. And so that gives us 2500 at an angle of 0 degrees is equal to I1 times 0.25 plus J2 plus I1 times 27.53 plus J5. So we get 2500 at an angle of 0 degrees is equal to I1 times 23 point or 20. Let's see. .27 plus 0.25 is I think Okay, inverted a number here.